Welcome back. We are discussing about wastewater treatment, under which we are talking about secondary treatment. In the secondary treatment, we will be talking about the trickling filter. We have seen earlier the activated sludge process, which is based on suspended growth process. Now we'll see the other option, which is used for biological treatment, called as a trickling filter. So this is mainly based on attached growth process. So here what we see, the preliminary treatment will not change. The screens, grit chamber, then primary sedimentation tank. Then in place of aeration tank, we are keeping a trickling filter. And secondary sedimentation tank is also following. But what thing is here also, there is recycling of the wastewater from after secondary sedimentation tank. The only difference is earlier secondary, this activated sludge process, we are recycling the sludge back into the aeration tank. Now the wastewater coming from the secondary sedimentation tank will be recycled back into the trickling filter because the sludge concentration is very, very small here. And the wastewater after the secondary sedimentation tank can be directly discharged into the receiving body. And sludge from primary and secondary, it can undergo sludge handling techniques. There can be thickener, there can be a digester, there can be a sludge drying beds and another dewatering systems, and subsequently goes to the final disposal. So the major important mechanism here is the attached growth process. What exactly is this? That we'll try to look at here. So now you see here, the attached growth process, the microorganisms that are attached to some inert material. This inert material can be a stone. You can see here in this picture, the large stones, coarse aggregate. It can be broken stones, broken bricks, and any other large surface where it have more voids. That is the more important thing here. You see here in this information shows the granites, stones, slag, plastic material, redwood slabs. They're having high void spaces, 45 to 60%, up to 97%. And then size also you see here around close to 50 mm, more than 50 mm like that. So when they are at the same time, they're also having irregular surface. Irregular surfaces means more voids. So now the mechanism is depicted here. This is the material and another material is here, right? In between, the water is flowing from the top. And the water is flowing from the top because the water in the upper surface is open to atmosphere. The air will come in contact with the water. So the surface close to the stone or the filter media, we can't say stone media, it's a filter media. The air will be coming in contact with the liquid, and then the surface close to the liquid and air, they will be under aerobic decomposition. There will be small portion here that will not receive the air completely. It partially undergo in the anaerobic conditions. But this layer is very, very small in thickness, and aerobic layer is only predominating. So the microorganisms receive the air from the atmosphere, and then they will decompose the organic solids in the wastewater, and they will decompose it into corresponding compounds of carbon dioxide and other aerobic decomposition products. So while the wastewater flows over the material, the biological action takes place. So now let us look at the construction. This is a trickling filter. Now you see here, this is a circular configuration and at the small height, cylindrical. Now what you see here is the influent is coming from the bottom and rising to the top. And then what you are seeing in the top is a distributory central column is there. It rises through central column. and then the rotatory arm is there. Rotatory arm is there. And now the entire filter, this is the filter bed. You can see here in the picture. The filter bed, as you said earlier, it is now with all the large spaced, large voids, filter material is kept here. And now the rotatory arm, there are four arms here. There are four arms here. And then they're going to distribute here. They're going to distribute the water is rising, and then the rotatory arms are there, and the arms are now connected with the string to the central column, and then the water will pass through the rotating arms here, and there will be some nozzles. These nozzles you can see here. The water will come out from the nozzle. This is the central column, and the central column is tied with these rotating arms with the strings, and water will come and then pass through this pipe, and then through these nozzles the water will start filling or spreading on trickling on top of the filter bed. Since the wastewater is trickling on the filter bed, it is called as a trickling filter. So the water will pass through, the wastewater pass through, and then go through the entire depth of the bed, and then there will be under drain system at the bottom. There will be under drain system at the bottom here, and they will be connected. The under drain system is there at the bottom, and water will pass through the filter bed and through under drain system, and it is collected through a effluent pipe. This is the thing. So usually the filter depth is around 1.2 to 1.8 meters depth, and 25 to 75 mm size filter medium we are going to use. So while the water is passing through the filter bed, as discussed in the previous slide, the aerobic reaction is predominantly taking place, and subsequently it will go the aerobic decomposition process. And occasionally, when the diameter or depth is more, sometimes we may provide also air vent pipes, which are nothing but perforated pipes. They are inserted at the circumference, inner circumference of the trickling filter. So the air will pass through that bed, that pipe here, and then through perforations, it will circulate into the filter bed at the bottom depths. So that aerobic reaction continues in the depth of the bed. So now you see here different configurations. This is the trickling filter where water is trickling, and this is the filter material. So now this is the entire view of the trickling filter bed. So now this arms will be rotating with very low speed in all the directions, so that the water will be sprinkled over the entire area of the bed. And now you see here, these are the under drain systems are provided here. So the water will be collected from the bottom openings here, and the water falls from the filter bed into these small openings, and then that will pass through the wide openings provided at the bottom, and they're inserted at a longitudinal slope towards this particular direction, right? So now sometimes the more void space to be created, then we're going to use a plastic material of this nature also. So here you can see here in this model, what we see is a large amount of surface area is also provided here when you're creating a voids. So in this large surface area, there's space where the bacteria to get attached on the inner surface of these openings. And this is where the efficiency of the process is going to increase. But if you see this, the aggregate, only the outer surface is available for the bacteria to get attached. But here, when you see the irregular surface inside, a large amount of surface area is also available per unit volume to get the microorganisms attached to this particular filter medium. Sometimes we also use this type of slabs, plastic sheets or slabs, where again having hollow spaces in between, so that the basic objective is to create more voids at the same time, more surface area per unit volume. Now, this is the layout of the trickling filter. This is the primary sedimentation tank, then trickling filter, then secondary sedimentation tank. Wastewater is passing through this system, and after the second sedimentation tank, the liquid will be going out. Some portion of this will be returned back into the system. Similarly, there is a high rate trickling filter where recycling is provided for intermediate system and second stage system. Here we define two terms, recirculation ratio and recirculation factor. Recirculation ratio is a ratio of recirculate flow to original inflow of sewage, QR by Q. Recirculation factor is the number of effective passes. So we can write down in terms of F is equal to simplified form 1 plus R by 1 plus 0.1 R whole square for sewage. Earlier, instead, they were having one more constant. So that is simplified for practical uses for sewage. We'll write as 1 plus R by 1 plus 0.1 R whole square, where R is the recirculation ratio. Recirculation ratio is nothing but recirculation factor, or R. We can say here is 1 plus R. Low rate or standard rate filters. And low rate filter, standard filter, the no recirculation is provided, and single clarified is provided before trickling filter. The high rate or two-stage trickling filter, recirculation is provided from 0.5 to 3 times. Two clarifier are also provided, then they called as a one stage or two stage. If only recirculation with one stage is called single stage high rate trickling filter. If two stages are provided with recirculation at each stage, they're calling as two-stage high-rate trickling filters. The major design parameters are BOD loading, are also called as organic loading. Another one is hydraulic loading. And when provide recirculation, what is the advantage? The hydraulic loading per unit area is increased, more continuous flows are adapted, and major purpose is to bring back the biological population treatment system to get the treatment system efficiency to be increased. It reduces clogging and dilutes the pollution load and reduces short circuiting of flow. So recirculation in the biological system will definitely help in reintroducing back into active biological solids into the treatment system, so that they will motivate the actual biological solids or microorganisms to increase the decomposition of organic solids in the wastewater, right? So this is all about the basics of trickling filter mechanism. This is based mainly on the attached growth process. Attached growth process means the microorganisms are attached to a particular filter medium. The fundamental criteria here is the surface area should be maximum and voids also should be maximum. Whereas in activated sludge process, that is based on suspended growth, where all the microorganisms, they will be floating or suspended condition in the wastewater tank or aeration tank. That is the major difference here, right? Thank you.